All right, today we're looking at chapter 5 in our book, which deals with thermochemistry. Now, thermochemistry is just the study of temperature effects in chemistry. Now, temperature can be more than just getting hot and cold, it's how it goes about getting hot and cold. Thermochemistry does apply if you just take a substance like water and boil it, but it also plays in if we do a chemical reaction to create that heat, like an instant hot pack or an instant cold pack. So thermochemistry pops in a lot of places. And what we're going to start off in this chapter is with just some definitions or some terms we're going to use to get the conversation going. So what I mean by that and all this, a thermochemical reaction could be something as simple as lighting a match. Now, that is an actual chemical reaction. On that match, the main active ingredient is typically potassium chlorate. And when you strike that match, that friction starts a chemical reaction where the potassium chlorate gets turned into potassium chloride, and then a bunch of oxygen is released. And we need to double that, double this, but that would make 3 oxygen molecules. Well, those oxygen molecules are going to be burnt immediately, but they're actually adding fuel to the fire because oxygen is very flammable. So it's almost like blowing pure oxygen onto that match where it strikes. Well, that initial reaction gets that going. Matter of fact, if you actually were to buy some potassium chlorate, it does look like a white powder, kind of like salt in its look. I think it looks a little bit shinier than standard old table salt does. But if you could actually make a little line with it and actually, if you got it hot or lit it on fire, the fire would travel along that line. You might have seen that in like Hollywood movies. They pour the powder and then set it on fire and it goes over and blows up the car. They're typically using black powder for that, but you will sometimes see potassium chlorate, which is a white powder, does the exact same thing. But it releases that oxygen as it burns. But it is a chemical reaction, and it just happens to be releasing a lot of heat when it goes forward. And that heat, along with the oxygen, helps sustain that fire. All right, that's one type of thing that follows into thermochemistry. There are others that actually fit into the realm of thermochemistry. Now, all of these are actually going to be energy from chemical reactions. Left that FE there for and we'll talk about that here in a moment. But first thing here, we got just a sandwich. Now, that's actually chemical energy, but when we consume food, the biological processes are going to break those bonds, move them around. Breaking in the bonds of the carbohydrates helps produce energy. The protein in there gets reused. So it's all chemically converted into things we use. And some of it is converted just flat out into heat or thermal energy. The next picture is a little bit more obvious that there's chemical energy going on. When we burn gas in our cars, obviously there's a lot of heat that comes out. That's why we have radiators. But it also produces a lot of gases, carbon dioxide gas and water vapor, and those gases expand in our pistons, make the engine go. So chemical reactions like that clearly have energy in them. It turns out that last picture, a lot of people look at that and thinking, oh, it's just molten iron. And it could be, but it's actually also molten iron oxide or iron ore. And all iron ores are various ratios of iron to oxygen. Sometimes the iron has a positive 2 charge, sometimes has a positive 3 charge. Those are the 2 most common charges for the iron. Sometimes it's O, sometimes it's OH, hydroxide, but it's always a ratio with some hydrogens and some irons and oxygens. And what they'll do in the smelters, when they're actually breaking that down, they have to get that iron ore really, really hot. And to help the process out, speed up the chemistry of it, they use carbon actually, from charcoal or coal itself, and that actually traps some of that oxide as carbon monoxide, which will later actually react and turn into carbon dioxide. And we even have some more modern techniques that trap all of that oxygen and the carbon as carbonates, so we're not releasing the CO2 in the atmosphere. But the carbonates actually produce some other issues, and it's not perfect, so they're working on that. They're getting more and more fun for the engineers. All right, Other forms of energy that fit into thermochemistry can be classified as just kinetic and potential. Now, what I have on the left, the waterfall, is kinetic energy. As that water falls down, it releases a tremendous amount of energy. Chemical reactions are kind of the same way, in the sense that reactant going to products, that forward reaction is kind of kinetic. It's actually going to go forward. It releases or absorbs energy, and as it goes forward. So that arrow itself is kind of like the kinetic energy. But we actually do have the potential to stop reactions. Like right now, my car sitting out in my driveway, there's gas in it. It has the potential of burning and actually making that car go forward. But there's no reason it has to. So it has chemical potential to actually do that. And that's kind of like what the dam is representing. The dam holds that water back. We can utilize that water pressure to turn the turbines and make energy. We might just use it to hold the water back to make a good fishing or a pleasure lake. Most of them have both purposes. You can get fishing out of it. You can actually enjoy it with boating. You can also do hydroelectric dam and get electrical power out of it. But multiple things we can do with potential energy. But technically, even though these are the dam especially is a mechanical thing, that can be related to thermochemistry. All right. When we talk about the thermal part, what we're really talking about microscopically is how much the molecules themselves are moving. Now, the picture I have here is just representing water, but it would actually apply to any substance. Hot water actually just flat out vibrates more than cold water. Doesn't necessarily need to move a lot more, but it does actually have a faster movement rate on average. But the biggest transition of that energy is just in those vibrations. Matter of fact, the standard household microwave, the only thing it does it really well, but it actually uses radio waves to cause water molecules to vibrate faster. And when the water molecules vibrate faster, they're producing heat or they heat up. And that's all a microwave really does, is just get water to heat up really, really well. Now, technically, that's what most of our cooking facilities do, but what you get different behavior in a microwave because the water is not necessarily evenly distributed through our food. And if you think about it, if you tried to microwave, I'm going to say bread or pizza, you might just notice that the crust gets a little bit thicker or harder. That really is because you're going to actually heat the water and the outside so much it just leaves the water, or it leaves the crust. And now it's all dried out and it's harder that way. Potatoes do the same thing. Anything that has that porous skin that has a slightly different water content, you'll actually typically dry out the crust faster. But thermal energy really just is those vibration of molecules. Now, in the chemistry lab, we measure those with thermometers, and thermometers are very effective means. Now, both these two ways, we don't really do these in the lab too much anymore. The alcohol thermometer, which is similar to a mercury thermometer here over in A, really just does have a liquid in a glass vacuum tube, and as you heat up that liquid, it expands. Now, in many cases, as these get old, you start to see weird things. You can see on this one, I put a little line on that. What I'm trying to show is that something that happens with alcohol and mercury thermometers. Since this is a liquid, it will occasionally vaporize, and it will occasionally condense. And sometimes you get these weird things where the condensation is above a little air pocket. And technically, these will both move together now. But that's created a small amount of error in that measurement. Heck, the other big issue, most of the time, these things are just kind of attached here kind of loosely. And if you don't like the temperature, you can actually grab that glass rod and just move it around. Right? It doesn't really change the temperature, but it does show that they're not super well calibrated. They're great for telling us how hot it is outside and such, but these aren't necessarily the most accurate way of measuring temperature. Slightly more accurate are these little coil magnets or coil thermometers. And what they do in a coil thermometer, they're going to have two different pieces of metal. This one is actually showing brass and steel. Now, being that it's two different pieces of metal, we find this cool little physical feature. Metals expand when you heat them up. Different types of metal expand at different rates. So if I have brass and steel wrapped around each other, and just so happens the brass has a bigger or expands more with temperature increases, we will see it move more. and that coil will get further. So what we'll do is we'll have this coil. We'll secure this one on like a post. This one over here, we could put a little pin on it. And what you used to see, old weather mappings, they'd run paper along here. And the paper would have little curves to match that curve it would go along. And that paper would just pull through about maybe 4 inches an hour. And then you could map that temperature and all those changes that go through over an hour. Used to see these all the time. I grew up north in Ohio, and weather things like ski lodges and such would be all these little things like this. So you can see what the temperature is any given moment. And they're mostly accurate, useful. You could tell if you saw temperature drop, blah, 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 et cetera, et cetera. But both of these have actually been replaced. And what I mean by replaced, we actually are starting to see a lot more electronic thermometers. This being a metal probe and just a little resistor in there, these are far more accurate, less need to recalibrate, and almost all of them have down to a tenth of a degree. And these are getting ridiculously cheap. This is one that I found on Amazon specifically for checking if you've cooked your barbecue well enough. You'd stick that in the beef or whatever you're cooking on your grill and measure the actual temperature. But you can get these for all different types of things. We even have them in the chem lab that look like they're maybe the length of a penny, and we can stick them down in liquids. And I have one that's all set up. I only have one of these. I don't have enough for all the students to use. But you put the thermometer down in your beaker, and then you tell the little sensor probe how hot you want it, and it'll hold it to that temperature within a tenth of a degree for however long you want. It won't vary at all. Just if you tell it to warm up a beaker of water to 80.4 degrees, it'll get it to 80.4 degrees, and it'll just stay there. It'll cycle the heat on and off as it needs, and the temperatures will be perfectly flat. So the electronics have really paid off if we want to produce that. But it's going to be more important for us to measure the heat, because it turns out measuring the heat, the temperature change, is more important for us in this chapter or this part of thermochemistry. All right, what I mean by that, we've been talking about heat and we've been talking about temperature changes. Turns out they're related. So heat is just a numerical value. It really is. How much is this container vibrating compared to that container? But when we actually heat up an object and add more vibrations to it, we're going to see that this heat is at least proportional to that change in temperature. Not the temperature itself, but how much it's going to change. So if you add a lot of heat to something, it's going to heat up more. If you add just a little bit of heat, it's going to heat up less. If you remove heat, you'd expect the temperature to drop, but we're going to see they're proportional. Now, they're not always proportional. So it's not like a certain amount of heat always gets you a certain amount of temperature change. And we can see this on something like maybe a pot of water on the stove. So if you were to actually want to make tea and boil water in a little kettle, if you were to put the kettle on the stove without any water in it, that kettle heats up really, really fast. But if there's water in there, it takes a little bit longer to heat up because the water has to absorb all that energy. So the amount of substance changes how much this relationship is. You don't get nearly as much of a temperature change based on the amount of the substance. Turns out the type of substance makes a difference too. Turns out water heats up a lot harder than almost everything. So even like a known measured amount of heat might make water warm up like a degree or two. Yet if you actually put that same amount of heat into the same mass of a iron skillet, you would notice that iron skillet heats up a lot more because the amount of heat that water can absorb before it changes temperature is a lot higher than most substances. All right, so let's talk about what we mean about this heat first so we can actually connect the dots on what we just introduced with that Q. So that transfer of heat, we're always going to say, goes from a hot body to a cold body. And we're going to say they need to be in contact somehow. And that's what they're trying to show here. We got an isolated hot container and a cold container, and they're isolated. There's a dead air space between the two. All right, so if that's perfectly dead air, this heat will stay the same no matter what, and this level will stay the same no matter what. The heat will not transfer unless there's contact between the surfaces. Even if it's a metal box, if the metal comes in contact with metal, heat can transfer through the metal. But if it's like a vacuum between these two, the heat will not be expected to transfer. But as soon as they're in contact, The higher vibrations on the hot side transfer to the lower side. We actually use the term and we say heat is what's transferred. So the heat gets transferred until we get the situation where they're both equal temperatures. We see this on something as simple as a coffee mug. You have coffee, you have you have a coffee mug, you put hot coffee in it. You're going to feel the heat through the mug relatively quick. And you do notice that certain mugs heat up quicker than others. And that really is related to what's between the hot surface and the cold surface. So the inside of the mug to the outside of the mug. Some transfer heat a lot more than others. All right, so that's just dealing with how it transfers. It always goes from hot to cold. The way we get heat can be very different ways. Right now I've been talking about burning stuff, heating stuff, hot plates, whatnot. We can actually get it from chemical reactions as well. We're showing a blowtorch here. This is an acetylene torch. What's oxyacetylene? Acetylene would do the same thing, just that would take a lot longer to burn through something like a steel girder. The acetylene just adds a bunch of oxygen to that mixture, so it burns faster. Great if you ever wanted to cut some railroad ties. Probably hard to get all the resources to do this. And you can go to Home Depot and Lowe's and get an acetylene torch, but an acetylene torch would take a while to cut through this. But it is just a combustion. It is burning things just like your gas in your car. It's just that particular chemical, the acetylene, releases a lot more energy as it burns. Now, next to that, I have a chemical reaction that gets cold when it goes forward. Now, this is kind of a neat thing. So this guy over here, we take some ammonium nitrate that is a solid. That's what that white powder is representing. And all we're going to do is rupture this bag of water. As the ammonium nitrate dissolves in water, aqueous, it absorbs a bunch of heat. So heat is kind of like a reactant. It just sucks it into the reaction and goes forward. The result of which that bag would get cold. It gets cold relatively fast too. It can actually even freeze that water, so it actually have ice crystals in it, which is why it's called an instant cold pack. Great if you're going to be camping in a trail and you want to take a first aid kit because ice can hurt if there's like a sprained ankle or something. And obviously, if you're hiking, you're not going to be taking ice with you. So an instant cold pack could be quite beneficial. But this is heat that's coming from a chemical reaction. It's either being produced, like when we burn something over here, or it's being absorbed in a chemical reaction like this. But chemical reactions can produce and give off heat. They are both happen. Exothermic reactions are reactions that give off heat. Endothermic reactions are reactions that absorb heat. And both happen. All right, on to how that size make a difference. Now, this is a better analogy than what I was probably describing because I got this actual picture. So what I have is a cast iron skillet. I got a big one and a small one. And I got a hot plate. Even if these hot plates could put out the exact same amount of heat, we all know that this one, being smaller, is probably going to heat up faster because there's less mass to it. Well, the heat capacity, that first term there, really is simply how much heat something can hold. And since this is bigger, it would have a bigger heat capacity. It can hold more stuff to it. But if I were to somehow take those heat capacities for both of these as numerical numbers and divide by their amounts, I would probably get the exact same ratio because they're both iron. So the heat capacity by its amount is going to be related to each other because it's the same material. Well, that specific heat capacity, what's talking about here, is, or specific heat, is that ratio that has the mass considered into it. Matter of fact, the units of specific heat capacity, or just specific heat, has joules in it, which is a heat unit, per gram per degree Celsius. So what that's saying is, we could measure how much this heats up if we knew for sure how much what its mass is and what temperature change it goes through. We could tell for sure how much heat that was. And we're going to do some math with that. Now, before we do it, I was going to look at some specific heat values. And in that previous page, I did have joules per gram Celsius. We're going to see that it's actually interchangeable. So water here has this value of 4.184 joules per gram Kelvin, it could also be 4.184 joules per gram degree Celsius. And we'll see why in a bit, why we don't have to worry about changing those units. All right. In addition to that, we have the same value but slightly different energy units. It turns out joules are a measure of heat, and so are calories. Now, calories pop in because these are kind of like our food calories. Not exactly the same. We'll expand on that slightly more in a bit, but these units both get used. Ironically, in your textbook, we're going to mostly be using joules, yet if you take organic chem, if that's something you end up taking in the future, you'll mostly be using calories. And that really has a lot more to do with the fact that these can be related to food calories. It's either easier to put that in perspective on energy levels if we can compare it to like a candy bar. All right, so we're going to apply this and get some cues first before we do anything at all with the calories. So if I wanted to find out how much energy, heat energy, something takes to warm up, I'm going to use a very specific equation. So the Q that we have, the heat of something, is going to be a product of the specific heat, lowercase c, times the mass times the change in temperature. So in this case, if I want to find this Q, I know the specific heat is for water, and even though it's not on this page, it was on that previous page. It is 4.184 joules per gram Kelvin. And that is something I'll be giving you. I don't expect you to have specific heat values memorized. The mass in this case is 800 grams. And the delta T, final temperature is 85 degrees Celsius. Initial temperature is 21 degrees Celsius. Now here's where we can see why Kelvin doesn't necessarily need to be changed to Celsius. Because really, if we think about it, since this says Kelvin, you might want to convert this to Kelvin, which means you would add 273 to this value and you would add 273 to this value. Well, if you think about that, 273 minus 273, it won't make a difference. What we actually can safely say, since we're dealing with a delta T, that can be kelvins or Celsius because a Kelvin degree is the same size as a Celsius degree. Or freezing point of water to the boiling point of water is 100 degree difference in Celsius. It's also 100 degree difference in kelvins. It just changes what these values are. So we can do this in either Celsius or Kelvin, and we don't have to convert one to the other. All right, to actually calculate this, we're just throwing this into a calculator. So I have 4.184 times 800. Oops, that won't be 800, will it? Times 85 minus 21. And really large number, we're going to put it in kilojoules. So this is 214 kilojoules. And even though that seems like it's a really large number, that is about right. This actually would take a lot of water, get a lot of heat. So 800 grams is quite a bit of water, a little bit more than a cup of water. And to go up 60 degrees would require quite a bit of heat. All right, let's do another one of these. Let's work a little bit backwards, though. I'm going to give you the heat. I told you that this particular piece of metal absorbs 1.43 kilojoules. And I tell you the temperature change it goes through, and I tell you the mass, and I want the specific heat. But we are going to use that same equation. We're just plugging different things in. Now, we are going to put our Q down here in terms of joules. So I'm just moving that decimal 3 places as I write it down. We're going to solve for the specific heat. We do have the mass of 217 grams. And our change of temperature, final temperature is 39.1. Initial temperature is 24.5. All right, let's see what we get here. I'm going to start with the left here. So 1430. And I will move this 217 over by dividing. So divide by 217. And then I'm also going to divide by the parentheses. 39.1 9.1 minus 24.5 close parentheses equals, I get a specific heat of 0.451. And the units will be joules per gram degree Celsius or Kelvin. On the test, I typically write Kelvin because that degree symbol is a special character on the keyboard. K is much easier to type. All right, to actually study this and to get all this, we're going to use something called calorimetry. Now, the big advantage to studying calorimetry is it takes into consideration a problem we'd have in the actual lab. What I mean by a problem, if we're actually going to try to study the heat exchange when you pour a hot liquid into a cup of water, for instance, we actually have to worry about the heat leaving that cup. Because think about that. If I put hot liquid in a paper cup, you feel the heat through that paper cup relatively fast. It's what's somewhat nice about things like Dunkin' Donuts. If you go there for coffee, even though they serve that coffee so hot that you can't drink it for like a year, you don't burn yourself by touching the cup because they use those insulated cups. All right, what calorimetry takes in mind is we want to minimize that loss of heat. So what we want to do is have all that heat go into a very specific location. So what I want to do, instead of losing that heat outside, we're going to have a magic beaker. And whatever heat goes into that water stays in it. So if I were to put a hot piece of metal into that water, that heat goes out into the water, but doesn't heat up the outside of that container. That's what calorimetry is. Now, I gave a tip off to what we're going to do. We need something really, really insulated. You don't want to use a paper cup for hot coffee. Styrofoam does a so much better job. Matter of fact, the easiest form of calorimetry is just to use styrofoam cups. You nest a couple styrofoam cups into each other, and that isolates that heat. So if I put anything into this container of water, all that heat gets transferred out just to the water and nowhere else. And that's what this is on this picture where it's talking about that. Whether it's a endothermic chemical reaction or a cold piece of metal or an exothermic chemical reaction and a hot piece of metal, no matter how we think about this, we're going to be losing heat going out to the surroundings, or we're going to be sucking heat in from the surroundings. We want to isolate this system from these surroundings and remove the possibility of heat coming from the outside. That's what that magic insulated box is for. Now, this is a theoretical thing. We're talking about a box that actually allows no heat to transfer whatsoever. And there really isn't such a thing. It'd be nice because if you had something like that, you wouldn't have to worry about heating and cooling your house so much because the sun wouldn't heat it up or cool it just by shining on it, because we wouldn't lose heat through our walls. All right, but we're going to see this with something as simple as this at first. And it turns out in the chem lab, this is what we actually use. And we know in the real world this makes sense, because if you put a hot liquid in a styrofoam cup, that cup stays cool on the outside. It takes a lot of heat for you to fill it through that container. And if I were to put two inside of each other, that's almost going to perfectly isolate it. Now, it's not perfect, because if it was perfect, a hot cup of Dunkin' Donuts coffee would never cool down. But it does transfer eventually. The styrofoam just slows the process. And at least in a chemistry lab setting, it typically slows it enough that we can actually say it is stopped, or at least it's within reason that it's stopped. Now, if you need something better, a little bit more precise or smaller temperature changes, they sell things that are called commercial calorimeters. Biggest difference here, these are all going to be made of metal, and what they typically can do is this inner jacket, we can typically vacuum the air out. Because if it's a true vacuum, there's no atoms whatsoever between those two layers. The heat won't transfer at all, because heat needs those vibrating molecules to move. If there's no molecules there, there's no heat transfer. These are the weird things. If you ever seen some of these coffee thermoses that you can put your hot coffee in it, put that lid on it, and it's still hot later in that day, those thermoses are typically working on something of this principle. just incredibly well insulated. There are actually vacuum thermoses, and they hold that heat really, really well for really long times. Matter of fact, when I was in grad school at the University of Florida, we used liquid nitrogen to keep these large magnets cool. And even though liquid nitrogen needs to stay at well under, well, or 100 degrees below Celsius, we wouldn't have to actually keep it refrigerated because we kept it in a dewar like this. The outer chamber was vacuumed out, so that cold nitrogen would stay liquid inside that. And we just have to we'd refill that dewar about once a week. We transfer into the magnets and get more in there, but we'd actually we were able to store it without actually having to worry about it heating up and boiling away. All right, so this is our idea that we're going to use in these calorimeters. And let's do it with a piece of metal to make sense of what's going on here. What I have this example is, I have a piece of metal that I'm going to put into my container that's full of water that's very, very hot. The metal's hot. What's going to happen eventually is the metal will cool down by heating up the water. Heat goes out into the water and causes it to heat up. All right, so we have this weird little relationship. Now, this is not saying that the Q is always positive for metal and negative for water. It's just saying they're always opposite sign. Because if you think about this, if the metal loses heat, the water must gain it. So they're always going to go opposite one another. Turns out in this case, how it's written, the metal is actually losing heat. So the metal is actually negative. It would actually be a negative value. And since the water is absorbing that heat and going up in temperature, the water is actually going to have a positive value because it's absorbing that. But they are opposite. But where this comes in real handy is water has a very, very, very predictable behavior. Has that really large heat capacity. It's easy to get the mass of something. Water is no exception. I mean, matter of fact, it's as simple as before we put the metal in there, we're going to empty out this container and weigh it, put water in it, weigh it again. Then we'd have the mass of the water exactly. And then with our temperature change, we're just going to get the delta T that the water goes through. And just because all of these things are easy to get, we're going to have the Q for the water very, very easily. And since they're equal to one another, we can actually solve, in many cases, for the specific heat of the metal. Because we could probably get the mass of the metal easily enough. You could find the temperature change the metal goes through. But we're going to find in most cases of calorimetry, especially when you're using a solid, you're going to actually learn more about the metal you put in than about the water. The water is going to behave very predictably with that 4.184 flat out with the mass. And it's going to be an excellent little resource because it takes a lot of heat to change it and temperature a lot. So our delta T's are never so high that we have to worry about it. It's not like it's going to boil the water with this piece of metal. Take a lot of energy to get water up to the boiling point. All right, let's look at a sample problem that does this. So what we have is we have a piece of rebarb, which is a type of steel, and we're going to put it into some water at 24 degrees Celsius. We're going to see that the final temperature goes up to 42.7. That is quite a bit of a temperature increase. That's a lot of energy to do that. We want to calculate the temperature the metal was initially. We're going to assume the specific heat of steel is approximately the same as iron, so it's 0.449 joules per gram Kelvin. And we're going to assume that all the heat transfers occurs between the rebarb and the water. We're saying it's in that perfect calorimeter that loses no heat to the outside. All right, we're going to start by just actually looking at this whole thing together. So Q equals Q. And we're going to remember their opposite signs here in a bit. So I'm going to put the metal over here and the water over here. And before I actually do it, I want to figure out which one's gaining energy and which one's losing. And you can see the water went from 24 to 42. So it went up in temperature. Since it went up in temperature, it's safe to say it gained energy. Therefore, the metal must be losing energy. All right, we're going to plug in a bunch of values, everything we know, and see where we get. So the specific heat of the metal, the first thing we're going to use is 0.449 joules per gram Kelvin. The mass of the metal is the next thing that goes in here, which is 360 grams. And then the temperature change the metal goes to. We know what it ends up at in its final state, 42.7, because both the metal and the water go to that final temperature. But we have no idea what its initial temperature is. Matter of fact, it says that's what it wants us to find out. Calculate the initial temperature. Right. On our right side with the water, we know the specific heat of water, 4.184 joules per gram Kelvin. Now, here's something weird. I didn't get the mass of the water. I have the volume. Now, that's an interesting thing that you would consider if you were really doing this in a lab. That volume was used because you wanted to have enough water in there that when you put the rebarb in, it would be totally covered. So that volume was just enough that it's going to have water on top of the metal when the metal's in there. But what should have happened, it's easy enough to figure out that volume based on just looking at how much water you would need. But it would have been more beneficial had you weighed it. So you'd weigh that calorimeter without any water. You'd add that 425 milliliters, and then you'd weigh it again, and get the mass that way. And we're going to pretend like we did it. Turns out the mass is roughly the same as the volume, so that's what I'm going to use. Now, this delta T we do know, because we know the water ended up as 42.7, and we know it started as 24.0. All right, one last thing I have to do, the opposite signs. All right, we're going to solve everything on this side, and then we're slowly going to move these other components over. We're going to isolate that Ti. That's what our goal is, to get it all by itself. So, and I'm going to let the calculator do all the work. So 4.184 times 425 times 42.7 minus 24. And that value that I get here is going to be the energy of the water. So about 33 kilojoules is how much heat the water absorbed. All right. Now to get rid of that, I'm going to divide by the 0.449 and by the 360. And this value here is equal to the 427 minus the Ti if it's a negative value. So I'm going to bring this over by how about we distribute that negative? So we'll add 442.7 to this, and that value should be my Ti because I've got rid of my negative that way. So my initial temperature is 248 degrees Celsius. Technically, since we're doing subtraction, I can use that other digit, so I should be able to say 248.4 accurately enough. That's typically how we end up using calorimetry with a physical object that we've heated up. So a straight out cooling down of the object or heating it up by heating it up with other means. Turns out we can do the same thing in a chemical reaction. And these can actually be kind of cool. Like this picture right here is showing something we call a chemical hand warmer. They're actually kind of neat because they're reusable. Now, if you lived up north and had to wear gloves a lot, this is something you might actually have because it helps. But what this is, when it's ready to go, it looks like a liquid inside a bag. And when you're ready to use it, you start flicking on this little disc, and that starts a crystallization to occur. And those crystals will spread and fill up that entire container, and once it's up there, it's releasing a lot of heat. Now, this is a neat little chemical reaction, because on the left, I have sodium acetate in that solution. It's technically a supersaturated solution, which does mean there's more in it than should be able to be dissolved. Turns out you can do that with sodium acetate relatively easy. So not really break anything. You're just physically we're able to make supersaturated solutions of that easily enough. It's just once we get the crystallization started back up, it's going to form, every bit of it's going to precipitate right back out. So on the product side, we still have sodium acetate still intact, but it's going to be a solid instead. It just so happens that this particular reaction, as it precipitates out, forms a lot of heat. Now, the big advantage to this thing, really, rather than compared to some of the other instant hot packs like this, is that this one's reusable. And all you have to do is, once this thing is cooled back down to room temperature, which it will eventually, you would actually put it into a container of hot water. So put it on the stove, gets the water hot, and it will return to this state. And once it's back here, you pull it back out and let it cool back down, and it's ready to reuse again. Pretty cool, huh? But it's a chemical reaction releasing a lot of heat. Now, there are others. A little bit easier one to deal with is just sodium hydroxide and hydrochloric acid. Doesn't release quite a amount of heat. But I have this one that actually does the exact opposite. Now, we talked about this one before. This was ammonium nitrate, that as it goes from solid to aqueous, it absorbs the heat, so it gets cold. But we have chemical reactions that produce heat, and we have chemical reactions that absorb heat. We're going to do a calculation with one that does actually produce heat. Now, it's not a lot of heat. If you notice, 22 to 28, it's only 6 degrees. Well, it's about 7. But we're not using a lot of substance, 0.1 molar and 0.1 molar. These are very dilute solutions, not many moles of chemicals being exchanged. Now, it is a neutralization reaction. We know that because water is a product, and we're making that from an acid and a base. Anytime you make water from an acid and a base, you have a neutralization reaction. And many neutralization reactions are exothermic. They produce heat as they go along. We have heat over here as a product. But not all are. Some are actually endothermic. All right, but this one's not super exothermic. Let's figure out how much heat's being produced. Now, you might think we need to do things differently, but since heat works the way it is, we are going to end up using the exact same Q. And we're going to use the exact same equation for it. So even though we've added these components, this mainly is still just water. So we just use the heat capacity of water. We would use the mass of the two solutions together. 50 milliliters and 50 milliliters makes about 100 grams. Because each, technically what we kind of see is in water, a gram and a milliliter are roughly the same amount. And then our change of temperature, we ended up at 28.9. We started at 22.0. You notice that equation and everything we wrote looks like what you would do if you just had 100 grams of water in a container and you somehow heated it up. And that is exactly what we're doing. We're just heating it up with a chemical reaction. All right, so what kind of value do we get? Let's see, 4.184 times 100 times, in parentheses, 28.9 minus 22. I get, I'll put it in kilojoules as well, so 2.89 kilojoules. So not nearly as much heat as we saw in some of those previous ones, but we're not seeing a large temperature change. Now, where this can be dangerous, if you imagine this is just 0.1 molarity and 0.1 molarity, if I were to bring those both up to like 6 molar, so more than 60 times on both these, you would get roughly 60 times the heat, because these are going to be proportional to that amount of energy in the amount of the moles. This could be dangerous. So when you neutralize very high concentrations of HCl with NaOH, you have to worry about the container getting really, really hot. Now, fortunately, there are other neutralization reactions get cold, and no one's really terribly worried about getting a reaction too cold, because it just, your container might freeze, but you don't have to worry about the hot liquid spilling on things and burning you or vaporizing acid or anything. So typically getting it cold is a little bit easier to deal with. Okay. When we start studying these in the chemistry lab and wanting to study them a lot more in depth on chemical reactions, we use this type of calorimeter. It's actually called a bomb calorimeter. Now, I know that name sounds pretty cool. As a matter of fact, one of these I got a chance to use when I was undergrad. The electrodes which fired this sample and actually cause it to burn. It was a weird little um, rod you held onto that had a button back here, had a little protected switch up here. So you had to you flip the switch up on the top and held that in place with one finger. A little light would come on in your bomb calorimeter, and when it turned green, you push this button, and when the green light went off, you let off. So it was all done to safely not blow up unless you really wanted the bomb to go off. And yet the irony is, the sample we put in there, you do all that, you don't hear anything. It's not like it pops. You don't even hear a spark. You don't hear anything. The only way you know something happened is the temperature changes. Now, this one actually shows one of those metal electrode temperature probes, but I'm old enough that what we had back in my day, it was one of those really tall mercury thermometers, very expensive mercury thermometer that only moved like 5 degrees. So, but very cool little setup. The one I got to use was previously owned by the CIA, so I'm telling what all they used it for. But that's how we do things when we want to get things like nutritional content on food. So we've all seen these things. Near the top, it always says the sample, the serving size. We're talking about a cup here, and it always tells you how much heat and calories that comes off when you consume it. Now, these calories are proportional to the joules we saw, but they're not the same as the calories we saw before, because I had up there that 4.184 joules per gram Kelvin was equivalent to 1 calorie per gram Kelvin, at least for water. And it turns out that 4.184 to 1 is the conversion of a calorie to joule. This calorie is not the exact same as that calorie. The difference is, if you notice, that's a capital C. And technically, anytime you see a food calorie, it should be a capital C, because a food calorie with a capital C is actually equal to 1 kilocalorie, or 1,000 of these lowercase calories that we've been talking about up here. Now, if you're in Europe and you find a nutritional label, they will typically list that in kcals. And it's not like we were, I don't know, I guess I've always said it makes it seem like Americans are lazy or too dumb to understand kilo. But the truth of the matter is, it has a lot more to do with the fact that when these started getting on every single container, kilos in America were always already associated with kilos of cocaine or kilos of heroin. And kilo was attached to drugs. And it created a small problem, so they just said calories. It's a little bit easy enough to deal with. All right, now here's something that's really cool. To get this value on something like macaroni and cheese, what they're going to do is cook up that 1 cup of macaroni and cheese, get it looking something like this. They would actually puree it, turn it into more like baby food, and they would put it into something like a bomb calorimeter and burn it and measure the heat that comes off. And it turns out 1 cup of macaroni and cheese is going to produce, on average, about 250 kilocalories worth of heat. And that's flat out where that comes from. There are people out in the world, that is their job on a daily basis. Is they take food, they burn it, record how much heat it gives off. Here local to us, there's actually a company in Gainesville that does that on restaurant food, like Chick-fil-A. Their chicken sandwiches, they'd cook a bunch of them up, puree them, burn them, figure out how much heat comes out of them. Be an interesting place to work, because you're technically working in a professional kitchen where food is not eaten. It just gets destroyed, burned, and measured for all these little nutritional contents. All right. We've actually introduced how we measure all these energies. What we're going to break down now is how to get those Qs, or those heat values, off of a chemical reaction. But we have a small problem with chemical reactions and how they lose their energy, because they don't just give off heat like this shows. Some of them also produce work. Now, what I mean by producing work in a well, if we were to think about your car, when you burn your gasoline, It does indeed produce a lot of heat. That's why there's a radiator in front of it. But that heat doesn't do anything to make the car go. What makes the car go and work is the carbon dioxide and water vapor that's being produced. It goes into your pistons, moves them up and down, and drives the little crankshaft in there. And that's to scale too. That's a perfect drawing of what your car looks like. Yeah. Now I could do that better, obviously. But combustion does both. It actually produces a lot of heat, but it also produces work. And that work is a form of energy. So if I wanted to study a chemical reaction, I'd have to worry about heat and work before I could get just the energy, before I could say it's just the energy of that reaction, because they're both going to be in there. All right, so in the chemistry lab, I would like to remove one of those two. And technically, since Q is real easy to get, I just need a thermometer and a scale to weigh it. I'd like to get rid of work. So we're going to introduce this term up here, enthalpy, that's going to help us study reactions where work is not a problem. All right, so let's talk about what's going on here so we can get some terminology in. Now, we said before that Q going into the system. So if we warm up the system by adding Q into it, that Q is positive. So heat going in is positive. Now that does mean that a reaction like the ammonium chloride, not the ammonium chloride, the ammonium nitrate, this is the one that we said ammonium nitrate, that should be a solid right there. Solid. Going and dissolving, this was the instant cold pack. So I'll just put over here cold pack. As that goes forward, heat is over here because it gets absorbed. So this particular reaction has a positive Q for the reaction, which always throws people off, because if you think about it, we're talking about something that gets cold and we're saying it has a positive Q. Well, the weird thing is, what we notice when we say it gets cold is what we experience, but we are kind of like the surroundings. So if the chemical reaction is getting absorbing heat, it's pulling it from the surroundings. So we feel the cold, while the energy increases in the reaction. All right, so that's that sign for Q. W actually has a different sign, but we do same type of thing. So we use the terms work on the system and work by the system. So if the system does work, like our cars, gas plus O2 gives carbon dioxide and water, and we all know that makes the pistons go. That's work being done by the reaction. That's going to have a, excuse me, I'm getting ready to sneeze. Pause the video so you didn't actually have to deal with that. All right, but in this situation, as it goes forward, work is being done by this chemical reaction. We're losing energy because it's dropping energy, doing the work. So we actually see the work is actually negative for the reaction. Now, little weirdness, if you're in physics, work has a totally opposite sign in physics than it does in chemistry. They always have, and they probably will for a long time, because of how we do our math. But here in chemistry, work being done by a chemical reaction loses energy, so it's a negative work. All right, fortunately, we're not going to do anything other than talk about work. We're not going to do any mathematical relationship with work in here, because we have introduced and are going to finish introducing enthalpy, which is going to get rid of the work term. All right, what I mean by getting rid of the work term, we're going to come back to this in just a second. Enthalpy is set up in such of a weird way. We're going to say the enthalpy is U plus P delta PB. Now, there's a reason we said P and B. We'll see that in just a second. Now, just like a temperature, it's easier in a chemical reaction to study a change. Temperature changes are easier to study because we can actually flat out measure them on a thermometer. Delta H's are actually easier to study too. So we're not going to study H and U and P and V. We're going to study the delta of all these. But we're going to put a cool little restriction right here. You notice how there's not a delta in front of P? Because what we're going to say is we're only going to study a situation where the pressure is held constant. Now, that's a safe thing to say that we're going to do, because if you think about the pressure in a lab at any given moment, it's not expected to change drastically because it's the atmospheric pressure. It will change throughout the day when storms come through, but we're not talking about rapid changes and we're not talking about drastic changes. So it is fair to say the pressure is held constant in most situations. But what this does is it reduces that term into this P delta V. This is a type of work. So what I mean by a type of work, let's think of a bicycle pump. And if I change the volume on it, so if I push down on that bicycle pump, doesn't it get harder as it goes down? Yeah, because the pressure's going up and we're making it work. Now, that's the whole work aspect here. So P delta V is a type of work. Matter of fact, it's the actually opposite sign here. It's P delta V is negative work. All right, where that comes in handy, since delta U was Q plus W and P delta V is just negative W, positive W and negative W cancel out. So what this tells us is if we study a chemical reaction at constant pressure, and it has to be something that doesn't produce a lot of pressure, we actually can safely say that that Q is totally related to the energy of the reaction. We're just going to not say it's the energy of the reaction anymore. We're going to say it's the enthalpy. It's the heat energy of the reaction. All right, that gives us a cool little restriction on that. We can totally ignore the work as long as we study reactions at constant pressure and ones that don't create pressure. Now, what I mean by that, back up here to our combustion reaction. If we were to put that a sample of gas in a container with oxygen and set it on fire, that container would build up pressure and possibly rupture that container. Turns out most combustion reactions do that type of thing when the gas molecules are big, like they are in our cars. We can't really study the delta H of these that directly because there is always going to be work involved with those type of reactions. But as long as there's not a lot of pressure change, we can study these and get a delta H on it. All right, I'm going to introduce this weird little term right now. It's a state function. Turns out delta H's for a given reaction are state functions. Reactants going to products are state functions. All right, what I mean by state functions, the heat that comes off of here is related to the relationship between the reactants and the products. And something kind of cool, if I deviate from that somehow. So let's say instead of going from reactants to products, let's go to some other mid reactant. So I will call it a subproduct or a reactive intermediate or just an intermediate. But once we get to the intermediate, we go on to the product. Turns out the distance or the change of energy would be the same regardless of how we get there, because delta H is a state function. It's related to the energy of this reactant and this product, not the difference in how you get there. It's kind of like the climb from the bottom of the mountain to the top of the mountain. The distance you would travel, or the altitude distance you would travel, is fixed because it's measured in feet from the sea level to the mountaintop. It's a fixed amount. The elevation is. How you get there is not, because it's possible that, like especially here in the United States, we have Pikes Peak. You can take a train to the top. I don't see many trains that curve a lot. So it is going to be a relatively straight path. But you probably can't walk that. Probably a little bit of an odd incline in places. And it's much easier to sometimes do these little mule train type paths, those little back and forth type segues they do when you go up and down a mountain. But no matter what, the difference between the peak and the summit are fixed on the elevation. They are state functions. All right, we're going to expand this whole thing here in just a second because they actually introduce a pretty cool feature for us. All right, so first thing I'm going to do is talk about a type of heat for a given reaction. So I have this reaction here. It's just the combustion of hydrogen. You take some hydrogen, you burn it with oxygen, out comes water. And turns out that that reaction does produce a bunch of heat. It produces 286 kilojoules of heat. So what is its delta H? Well, its delta H is actually this value, but since it's being produced, it's actually a negative value. And it's not just kilojoules, because it's related to what we make. Like, for instance, since this is only making water here, I'm going to compare it to water. I can't just say it's per mole of water, because it's not 286 kilojoules per mole of water. It's for every 2 moles of water. All right, what we see happen, because we would like to get a single number here, is we're going to see a lot of times where we want to show only a single product. And to do that, we actually have to have fractions sometimes in our balanced equations. And I know on every single previous chapter we had said you can't have fractions in there. Well, I lied. We can now. And we do have them in these type of reactions, because what I'd rather have for a delta H is a single value and not a fraction. So I really do just carry out that math. 286 divided by 2 is 143. And that is kilojoules per mole of water. And there's just that single value. And we're going to see that happens a lot. When we do combustion reactions like this, we actually can say that the heat of combustion for water, or the heat of combustion of hydrogen, is just 143 kilojoules per mole of H2O. And we don't have to give that whole balanced equation there, because you know it just wants to make a mole of H2O, as in 1 mole. All right, let's look at some other examples of these. We're going to look at real quickly some other combustion reactions, just to see what type of reactions we see. All right, so if you notice here, it says the combustion of carbon, and it gives this delta H over here. As a combustion of hydrogen, it has this delta H. Now, what we're going to see in the balanced equation, since it does say carbon, we do want to balance the equation with only having 1 mole of carbon. We're showing combustion, so we mix the carbon with the oxygen to make carbon dioxide, because that is a good combustion reaction for carbon. Same with hydrogen, we get water, but we're saying 1. Now, if I want to do it for magnesium, I'm going to take the magnesium, 1 molecule of it, or 1 mole of it, and I'm going to combine it with oxygen, because that's what combustion is. Now, what gets tricky here is you'd have to know what it makes. Now, sometimes that's easy. A lot of combustions of things with carbons in them make carbon dioxide and water. This one didn't make water because there's no hydrogens with that carbon. Magnesium oxide and many of our nonmetals are easy to predict, or many of our metals are easy to predict, because magnesium always likes to make positive 2 ions. It's going to make MgO. So I'm going to need half of these. But can't really do combustion of sulfur too easily, because it does make a sulfur oxide, but is it sulfur oxide, sulfur dioxide, sulfur trioxide? It's just safe to say there's an X and a Y here, and it varies. So to know exactly how this value came from, you'd almost need to know what product it actually makes. We're going to see heats of combustions aren't that popular. We're going to mostly focus on heats of formation. Now, a heat of formation is actually kind of cool. So in the back of your book, you have a big, huge table, and we say these are all heats of formation. So at the top of this column, delta HF, kilojoules per mole, and that's what all these values come from. They're just heats of formation for all these different compounds. Now, for CO2, gas, it should say gas there, it happens to be 393.5 kilojoules. What a heat of formation reaction looks like is we're going to make just 1 mole of this as a product. Whatever is given is the only product you have. And you're going to make it from the elements in there, in that molecule, in their standard state. Standard state is the most stable state at room temperature. for any of your metals in the periodic table, it's just the metal as a solid. So if I wanted to make sodium chloride, the metal is sodium solid. Nonmetals, we're going to find them in their most stable state. Up here, chlorine you find as Cl2 gas. Same with oxygen here. We know oxygen is probably O2 gas. And that's actually what it is. That is standard state. All right, but the carbon is a tricky one. How do you find carbon when it's all by itself? It turns out the simplest form that we find it is, or the most common form maybe, is graphite. If you think about carbon, you have graphite and diamond. Standard state is the more stable of the two. And it turns out for carbon, it is actually graphite. Now, once you have your standard state elements, you balance it based on what you want. So I want 1 carbon and 2 oxygens, 1 carbon and 2 oxygens. Up here with the sodium chloride I did, we have 1 sodium, but I only want 1 chlorine, and this was Cl2, so I'd put a half there. And that's why we end up using heats of formation, because we're able to generate the equation so much easier than, say, a heat of combustion. All right, now that we introduced some of these delta H's and how these values come from, let's see how we get them experimentally. So this particular acid-base neutralization reaction is the one we had up before. Matter of fact, it's the same numbers. So that 2.9 is what we calculated before. That's the heat produced as it goes forward. We want to turn that into a delta H. Turns out it's kind of easy most of the time, because that Q is part of our delta H, 2.9 kilojoules. We just need to relate it to the moles being produced or used up. So sometimes you have to worry about limiting reactants, but if you notice, these are both 0.05 moles. So this would be 0.05, and this would be 0.05. And if you think about it going completely forward, nice little 1-to-1 ratio, you would end up making 0.05 moles of sodium chloride, because every bit of this chlorine and every bit of that sodium makes 1 sodium chloride. So to get this delta H, we're just going to divide by 0.05 moles, because that's how much we're making. All right, and one last thing. Heat's being produced. Heat is over here. Heat's being produced. The reaction loses heat then. And therefore, the heat of this particular reaction is just 2.9 divided by 0.05. And that has 3 significant figures. This has 2. You can safely say 2 significant figures here. So 58 negative kilojoules per mole is the delta H for that reaction. So we can get it experimentally. We can get it from these tables in the back of the book. Well, these tables in the back of the book. And we can get it from other sources. Anytime you find a delta H, it's actually coming from a specific reaction. All right, so back to our slide. Let's actually apply this to something kind of cool. Now, I said earlier our delta H's are state functions. That was actually proven by this guy named Hess. And all he really proved is this cool little reaction. So if I were to take some carbon and burn it with oxygen, it does indeed make CO2. But the danger about burning anything like your car, carbon, when there's too little oxygen, is the creation of carbon monoxide. That's what they're showing here. So turns out carbon can also burn with too little oxygen to make carbon monoxide. It's still a gas, but this is only like half as much oxygen. Now, you typically would see the fire just go out if there's not enough oxygen, but as it's burning fewer and fewer, it does make more and more CO2. And even your car, as good as it's running, it produces a small amount of CO2 just because of the nature of combustion and those high pressure pistons. Fortunately, carbon monoxide in the atmosphere doesn't last very long, because it's also going to bump into O2, and it happens to make CO2. Just happens to be another half of an oxygen to do that. Because if you think about that, CO plus 1 O will give you your CO2. All right, Turns out these two reactions end up doing the exact same that top reaction does. Matter of fact, we can see that they kind of add together. If you somehow added this equation to this equation, everybody, the CO turns into that CO and it goes away. So we'd have carbon and one oxygen makes CO2. Since those two reactions add together, their delta H's add together. And that's what they're showing here. That 393 is for the full normal reaction. Each of these individual steps, 111 and 282, we add those together, we also get 393. All right. As neat as that is, where that really translates to us having a neat little benefit is we don't always have to study dangerous reactions. What I mean by that is that one we just had on there. This particular reaction would be something you'd not want to study directly because chlorine fluoride, fluorine, chlorine trifluoride, all three of those are relatively toxic compounds. So actually studying that reaction directly would take some special skills. And especially if you only want to get the heat of the reaction, that would almost be dangerous because you don't have any idea if it's exothermic or endothermic because we have no idea how to prepare for it. So before we even consider studying it, we might want to predict what that delta H is. And what we could do is just get a tabulated group of chemical reactions that have similar reactants. So what we're looking for is these guys down in some other reactions that have similar compounds. And we do. If you notice, I got F2 right there. I have COF right there. I got COF3 right there. And all of these have oxygen involved in them. You can see some common compounds and such, but there's a lot of common molecules. So what HASS would have us do is try to relate those three equations below to that over one above. And that's what we're going to do. Now, the neat thing is, as I kind of underline the species we want to do, we're going to actually try to make them look like this. So in this overall reaction, I have just a chlorine fluoride. And in equation 2 down here, I have a chlorine fluoride. I actually have two of them. Well, we just said we can do fractions in here, so I'm going to multiply every single one of those coefficients by half. So it's not two chlorine fluorides, it's ClF. And it's not O2, it's actually half of an O2. And it's not Cl2O, it's half of a Cl2O. And I do need to put phases here, they are important. And it's not just OF2, it's half of an OF2. All right, so we just distributed that half. Going to do same thing with the F2. I want it as a reactant. I have it here. There's a 2 in it in front of it in equation 1. So I am going to actually do the same type of thing and multiply everything by a half to get rid of that 2. But you'll also notice how this is a product. I want it as a reactant. So I'm going to reverse the equation. So I have just a single F2. And now half of an O2. And those go to make just one OF2 gas. And then my last component is this particular product, the ClF3. And I have it right there in equation 3. But if you notice in equation 3, it's a reactant. I want it to be a product, so I'm going to reverse equation 3. So I have half of a Cl2O. I have 3 halves of an OF2. This gives me a ClF3 and an O2. Gas and a gas. All right, before I do anything else, I want to actually make sure if I add these 3 equations together now, after I've manipulated them, I want to make sure everything that's not supposed to be there removes. I want to make sure it turns into this. What I mean by not supposed to be there, or that remove them, you notice I have half of an O2 right here, and I have half of an O2 right here. Half and a half is 1 O2. I have 1 O2 as a product. So it turns out those all cancel each other. And we can see the same thing happens with these 3 halves of an OF2. 3 halves and 1 plus a half cancel out. And then half of a Cl2O and half of Cl2O cancel out. Only thing left over is that ClF, the F2, and ClF3, the components we actually want. So because we're able to cancel things out, Hess would tell us we can combine these equations to give that. Therefore, we can combine these delta H's. And I can't just combine them like they are. I have to do what I did to each one of these. So since equation 2, since I multiplied all the coefficients by 1/2, I'm going to multiply this value by 1/2. And since equation 1, I did 1/2, I'm going to actually also multiply it by 1/2. But I also reversed it. Here's something neat. I can reverse this equation by just reversing the sign on my math. And then equation 3, the only thing I have to do is reverse it, so I'm going to make that a negative value. So it's not positive anymore. All right, now we're just going to add these 3 values together. So what I mean by that, I have positive, I'll clear this out, positive 49.4 times 0.5 plus 214.0 times 0.5 minus 236.2. I get the delta H is exothermic negative 104.5 kilojoules. All right, as neat as that is, the only way this works is if we have a whole bunch of reactions. Because heaven forbid I have 3 or 4 that have F2 in it. You have to find one that has common products to all those others, or common reactants. So this can be harder to do. Slightly easier way is to actually use those heats of formation from the back of the book. We're going to use that to do the exact same equation. The neat thing about using heats of formation to balance the equation is we know the delta H of any reaction is going to be equal to the sum of the delta H's for all the products minus the sum of the delta H's for all of the reactants. Now, when I say all, what I'm saying is if these had coefficients in front of them, if there's 2 ClF3s, we'd have twice the heat of formation for the ClF down there. But this is a nice 1-to-1-to-1, so we're just going to have, for my heat of the reaction, 1 times the heat of formation for the ClF3. That would be our only product, minus 1 times the heat of formation for the ClF, and 1 times the heat of formation for the F2. Only thing I need to do right now is get to the back of my book and get these heats of formation. They're easy enough to get. It's back of the book, they're in there alphabetically. So chlorine fluoride, ClF, has a heat of formation of negative 45.48. Negative, I said 45, but it said 54, didn't it? Yeah. 54.48. And that's going to end up going right here, negative 54.48. And chlorine trifluoride, also from there, is negative 158.99. Now, we do need fluoride because that's the other reactant, but if you think about this, F2 as a gas, what do you think is special about that? Well, if I go here to my book and find F2 gas, it has a heat of formation of 0. Matter of fact, if you notice the top of each of these is 0. It really is because F2 gas is standard state, and all standard states have heats of formation of 0. So I will, on the test, give you those 2, but I would have actually intentionally left fluoride off. It is because it's 0, because it's standard state. All right, so that makes this math a heck of a lot easier because I just start with the negative 158.99, and I'm going to minus a negative, so add 54.48. I get the exact same value, 104.51. All right, both ways give us that heat of formation using the heat of a reaction. Using the heat of formation from those tabulated values in the back of the book is typically much quicker. And Most people find it easier to follow than to actually do this. I would recommend review this a couple times to let it sink in and practice it. And I hope to have a couple of these on your practice tests so you can get a chance to really practice it. There's also some in your book to look at. All right, that finishes up with this chapter.